Earthquakes are caused by the energy released when two tectonic plates slide past each other on the Earth's crust. The magnitude is the energy an earthquake releases, and the intensity is the degree of shaking produced by the event. The Ring of Fire is responsible for 75% of the world's earthquakes, which is where Chile is located. Not only do earthquakes have immensely damaging effects themselves, they also cause tsunamis. These catastrophic events were seen firsthand in 2010 in Chile. On February 27, 2010, they were hit with a magnitude 8.8 earthquake, leading to over 500 casualties and causing damage to nearly 400,000 homes. 150 of these casualties were from the tsunami that followed. There were also hundreds of aftershocks in the following weeks, reaching up to a magnitude 5. This event displayed exactly why earthquake engineering and seismic structural design is so important, as earthquakes cannot cause casualties, but the failure of our buildings can. Earthquake engineering is the use of civil engineering to reduce damage and casualties due to earthquakes. We looked at the role of structural engineering to create seismically safe buildings. As civil engineers, we must create structures that are designed for controlled damage rather than to never collapse. There is only a 10% chance an earthquake will hit in a building's lifetime, so this is to reduce costs but keep them life-sustaining. Structures with high ductility provide the most safety as they can sustain a load for a long time, giving time to escape. To gauge a better understanding, we applied this knowledge to the structures we created of the Alto Rio building. Through this, we learned the importance of bracing strong columns and connections to create a safe structure. Therefore, in order to create seismically safe buildings, we must follow a simple design criteria. Pick a safe site. This is to avoid geotechnical failures. Have an adequate lateral loading system. This transfers the lateral forces from the top of the building to the foundations. Ensure regularity in elevation, stiffness, and mass to avoid a soft story failure. Strong connections between structural elements, which is connecting and anchoring of reinforcements and using appropriate materials. Use capacity design. This controls the failure of the building, making it more life-sustaining. We also look at the role of geotechnical engineering, which concerns the behaviors of earth materials to avoid liquefaction, landslides, and many other failures. Seismic slope stability. In order to understand this concept, we carried out experiments of the friction angle of granular soil. This is the maximum inclination of a slope formed by dry granular soils under gravity loading. A landslide of granular soil can take place when the shear force of the soil is higher than the friction force. If the friction angle is larger than the slope angle, then it's deemed stable, and if that's not the case, then it is unstable and is more likely to cause landslides. The looseness of soil can also cause instability. The more compact the soil, the higher its cohesive strength. The strength of a cohesive soil is given as a result of its friction and cohesion. Finally, we have liquefaction, which is when saturated soil starts behaving like a fluid. This is very unstable and can compromise the foundation of the building, causing it to sink or tip over. In conclusion, to help avoid casualties like those experienced in the 2010 Chile earthquake, we need to employ structural and geotechnical safety measures. Learning from these events can show us the best ways to design and build as we move forward and highlights the high level of responsibility that civil engineers hold.